contacts, and I explained to you what electrical machines are, because this course is about workshop by electrical machines. In our next contact, we're going to talk briefly about workshop before we conclude. So I'll explain what an electrical machine is. That an electrical machine is a device that can convert either mechanical energy to electrical energy, for example, a generator, or electrical energy to mechanical energy. You know the principle of energy conversion, that when this energy can be converted from one form to the other, but it cannot be destroyed. That we know that theory from primary, so from junior to secondary. So electrical can be converted to mechanical. That is electric motor. Then mechanical energy can be converted to electrical energy. That is a generator. So, and I listed examples of mechanical electrical machines. I said a transformer is one of them. Electric motor is one of them. I said like this puppy machine, transformers, etc. The example of puppy machine, example of electrical machines. And I explained some laws. I explained Faraday's law. I explained Lenz's law. I believe you all have all those laws. You have them at the back of your, you have them in your notebooks. And so you should know all those laws. So now we have talked about transformer exhaustively. So I will not need to, because of our short time, I will not need to be talking about transformer today. I have to go to generators. But before then, I can briefly explain some things in transformer. It was in this transformer I explained to you what is Faraday's law of induction. Is it clear? I state Faraday's law, which I said you can go to physics textbook and also simplify it. It's going to be simplified there. I said that Faraday's law states that if a flux passes through a turn of wire, that is a coil of wire, they call it solenoid, a voltage will be induced in the turn of wires that is directly proportional to the rate of change in the flux with respect to time. Is it clear? I explained it to you. That is the basis of a transformer action. Then you will see it in the material. I believe Mr. Yomi will share the material. So, but for today, we will be talking about basis of generator action. You know what is called a generator? We have even this generator we use in our homes. There are other generators, but what makes a generator is the ability to convert mechanical energy to electrical energy. Is it clear to you? The ability of any device to convert mechanical energy to electrical energy, that makes it to be a generator. So when we say generator, it's not just this made in China, Elepac, Sumek, Fiman, or Honda or Yamaha. That is not what we mean by it. Those are generators because they convert mechanical energy to electrical energy. But there are other generators that, for example, in drilling and oil production, we have what is called downhole generators. Downhole generators that provide the energy that is needed for what is called a downhole equipment, that are giving signals to surface equipment to know what is going on inside an oil well. Is it clear to you? So a generator basically is a device that converts mechanical energy to electrical energy. Please write it down. So what is the basis of a generator? That is, in a nutshell, how does a generator work? The basic principle, working principle of a generator. That's what we're talking about, basis of a generator action. So now, a wire moving through a magnetic field has a voltage induced in it. Mind you, I'm talking about the working principle of a generator, how generators work. Those generators that we are using in our homes now, how were they constructed? It's not just the frame of a generator that is the generator. Is it clear to you? Every equipment, every machine has the major components. Is it clear to you? Plus auxiliary components. The major component is where the working principle of that equipment lies. Is it clear to you? So now, the basis of a generator action is that a wire, that when we say wire now, we are talking of a conductor. A conductor moving through a magnetic field. You know what I mean by a magnetic field? I explained it that last week, that a magnetic field is a region around a back magnet where the magnetic force can be felt. Is it clear to you? So when we are, so all these things should not be strange to you. So a magnetic field is a region around a bar magnet where the magnetic force can be felt. I remember I was making an example with metals around the bar magnet, that if the metals are very close, the magnet will pick them. But if the materials are far from the magnetic force will not get to that area. So that is what is called a magnetic field. So a wire moving through a magnetic field has a voltage induced in it. A wire moving through a magnetic field has a voltage induced in it. I'm going to explain the meaning of induction. Is it clear to you? So that you people will really understand what we are talking about here, because this course is somehow technical. So now what do we mean by induced in it? Now, if you take a magnet, a bar magnet, for example, and you put a nail or any other metallic object on it for days, you put a nail on it or razor blade for days, for some time, it's just there. You didn't remove them. When you remove that nail from the magnet, the nail itself will turn to a magnet. I don't know if you have experimented it before. What we mean, what happened to that nail? That nail is not actually a magnet. What happens to it is that an induced magnetism. There is an induced magnetism on the nail. So that nail will be able to magnet other substances for some time. But after some time, you see that it turns to another normal nail or normal metal. Is it clear? That what I mean by induction. So a wire, that is a conductor, moving through a magnetic field, has a voltage induced in it. Is it clear? So if the wire circuit is closed, a current is induced with a direction determined according to Fleming's right-hand rule. This is the basis of generator action. Mechanical energy plus magnetic field equals electrical energy. It's very simple if you understand your physics very well. Is it clear to you? Everything you are now seeing in a generator, you are seeing the construction of a generator, very big generator. No matter how big a generator is, whether it's a Lister, whether it's a Meccano, whether it's all this I pass my neighbor generator, the basis of that generator is that a wire is moving through a magnetic field. Is it clear? And that wire that is moving through the magnetic field has voltage that is induced in that wire. Is it clear to you? So if the wire is now put in form of a circuit, a closed circuit, then a current is induced with a direction determined according to Fleming's right-hand rule. I'm going to explain Fleming's right-hand rule later as we progress. This is the basis of a generator action. So mechanical energy plus magnetic field will give you electrical energy. Is it clear? So you see your bulb on, you see you are playing music, you are using your electric kettle, you put on your television, you put on your heater, water heater, you put on all sorts of electrical devices in your home, because mechanical energy plus magnetic field has been converted to electrical energy. Is it clear to you? So the mechanical forces must act in a magnetic field for the induction to take place. Is it clear? In a closed circuit for electrical energy to be generated. So that is the basis of a generator action. That is how a generator works. When you buy fuel, you pour it in the generator, you on it. So every other component of a generator are auxiliary components. Is it clear to you? So now, what I've just explained to you now is called the mechanism. I don't know if you are following. What I just explained to you now is referred to as the mechanism, which is the foundation, the main component of any equipment or machine. All machines have the basic component. So that basic component is called the mechanism. Name it. Is it a car? A car has a basic component that is called the motor. Television have their basic components, but you see other components like screen, you see the buttons, those are just auxiliary components. The main component is the foundation of that equipment. So the foundation of a generator, the foundation of a generator is mechanical energy plus magnetic field that gives rise to electrical energy when we put it on. So a wire is moving through a magnetic field that has a voltage that is induced in it. If that wire is now closed circuited, a current is induced with a direction that is determined according to Fleming's right-hand rule. That is the basis of action of a generator. So now you will know that in Fleming's right-hand rule, your forefinger It's like when you would have done these things in physics, you stretch your right hand, and you have the thumb moving up, you have the finger that is close to the thumb stretch forward, that is called the forefinger, is stretched forward, that is the magnetic field. Then you have the middle finger is pointed down. The middle finger is pointed down, while the thumb is pointing in an adjacent position. That is the motion of the conductor. That is the wire. Is it clear to you? Then the forefinger is going straight. That is the magnetic field. Then the index finger, that is, or the middle finger, that is now coming down, is the induced current. Is it clear? That is Fleming's right hand rule. That is the basis of Fleming's right hand rule. So I've explained to you the basis of generator action. So we take another. We are going to take the basis of action of electric motor. So we quickly take that one and we proceed. Here now, we now go to the basis of electric motor action. That is, when we are talking of electric motor, I've explained to you that, for example, a pumping machine, for example, is an electric motor. Is it clear? Many electrical components, electrical machines, they have this electric motor. Is it clear to you? So now, what is the basis of motor action? A force is induced on a current carrying wire. It's almost the same thing. A force is induced on a current carrying wire that is placed within a magnetic field. I've explained how this force is induced when I told you that when you put a nail on a magnet, a bar magnet, for days, the nail itself will become a magnet temporarily. So that's what is also going on here. A force is induced on a current carrying wire placed within a magnetic field. The direction of the force is given by Fleming's left-hand rule. Is it clear to you? So you can see that the action of electric motor and the action of a generator are just the opposite of each other. If the index finger of the left hand points in the direction of the current vector and the middle finger points in the direction of the flux density vector B, then the thumb points in the direction of the resultant force on the wire. I'm going to explain this again because I think I'm fast. Yes, so I'm now talking of the basis of electric motor. So most of you that have worked before, maybe you have worked in electrical companies or mechanical companies, or electromechanical companies, electric motor is not going to be a problem to you. But I'll give you an example of an electric motor that a pumping machine, for example, that is pumping water from a borehole is an electric motor, for example. It's an example of an electric motor. That is the basis of the action of a pumping machine is electric motor. Is it clear to you? So I said a force is induced on a current carrying wire placed within a magnetic field. The direction of the force, that force that is induced on that current carrying wire, the direction is given by Fleming's left-hand rule. I've told you Fleming's right-hand rule. Is it clear to you? Now, we are not talking of Fleming's left-hand rule now. If you go to physics, you will see all these things there. They are not strange. Fleming's right-hand and left-hand rule is there. Now, if the index figure of the left hand, and you know the index figure, that is this big finger. If the index finger of the left hand points in the direction of the current vector, and the middle finger points in the direction of the flux density vector B, then the thumb points in the direction of the resultant force on the wire. Is it clear to you? So that is the basis of the working of an electric motor. Is it clear to you? Now there are diagrams to show all these working principles of either electric motor or a generator. There are diagrams, there are equations. So, but I'm going to continue. If a current carrying loop is placed in a magnetic field, a torque is produced, that is a rotation is produced, which causes a rotational movement of the loop, which is the basis of motor action. Is it clear to you? what this implies that the base of electric motor action is that electrical energy plus magnetic field will give you mechanical energy. You can see that it is the reverse. It is the reverse of generator action. So the basis of the working principle of electric motor is electrical energy plus magnetic fields to give us mechanical energy. Is it clear to you? That is electric motor principle. That is the principle. Is it clear to you? Let me that is in the material, and we have which we may not explain. So the next we are going to talk about is now. Most of us have electricity in physics. We'll be hearing of what is called DC generator. You'll be hearing of AC generator. Is it clear to you? Now, all these electrical companies, where you are hearing of Tesla, you are hearing of Faraday, and what they work, the basis of all this DC and AC generator are the works of Tesla, Faraday, and other pioneers in the field of electricity. Now we have DC generator, we have AC generator. DC means direct current. AC means alternating current. Is it clear to you? So we are for so far so good. We talked about the working principle of a generator. We talked about the working principle of an electric motor. I've told you that the working principle of it is basically based on Fleming's right hand rule, where mechanical and magnetic field leads. I believe it's it. You can do more research. That is, and I've told you that when we're talking about these generators we have in our homes, there are other smaller generators that generators downhole equipment in a drilling program. Please, you can go in a drilling program. I'm talking about electric motor, where I basis of the principles of electro, where I took electrical energy plus magnetic field gives you mechanical energy. Is it clear? And it's also based on Fleming's left-hand rule between a generator and an electric motor. Their working principles are different. Why the electric generator is based on Fleming's right-hand rule and energy conversion from mechanical plus magnetic field to electrical energy. That of electric motor is based on Fleming's left-hand rule and is the energy conversion from electrical to plus magnetic field equals mechanical energy. So I'm through with those two subtopics. Current generator, is it clear? Machine and electrical DC can convert mechanical into direct current electricity. Is it clear? DC machine can convert mechanical energy to current electricity. Now that's mechanical energy. I'm now telling you that mechanical to direct current electricity. You should be thinking of you should be the working of generators energy to energy. But for it. So an electrical DC machine can convert mechanical. We are talking of the DC generators now, please. Can convert mechanical energy to direct current electricity DC generator, or vice versa. Is it clear? Vice versa means that mechanical DC machines can convert electrical energy into mechanical energies. So that is DC motor. So we have DC motor, we have DC generators. It's the same work. The working principle I gave to you earlier. That is what the two of them work with. So without any construction changes, is it clear? Thus, a DC generator or a DC motor can broadly be termed as a DC machine. I'm going to take time to explain this because I'm not seeing you physically. You people may not understand it basically. Yes, so I'm going to come again. I'm talking about DC generator now. I said an electrical DC machine can convert mechanical energy into direct current electricity. Direct current. There's alternating current and there's direct current, that is AC. Is it clear to you? We have both AC and DC, though DC being more popular, but AC is more complex and more in use in a complex situation like factory setting. So that is a generator, or vice versa. The reverse is the case for DC motor. If you know that DC motor converts electrical energy to mechanical energy, and generators convert mechanical energy to electrical energy, you should know that when we are talking of DC generator, then DC motor is going to be the opposite also. Is it clear? So a DC generator or DC motor can be broadly termed as DC machines. So the two of them are direct current machines, whether it's a generator or a motor. Now the diagrams are here where you have what is called the components, the major components of a DC machine, whether it's a generator or it's a motor. You have what is called the stator. The stator is the two side of the magnet. You have the north side of the magnet, you have the right side of the magnet. Then you have what is called, then you have the magnetic field at the center. Then you have the brush. Because with this magnet, an electrical circuit is going to be created. Don't forget, we are going to have an electrical circuit. In that electrical circuit, what is called, they call it carbon brush. Most times they call it carbon brush in some textbooks. You have the brush, you have what is called the solenoid, which is the coil of wire. Then you have what is called the commutator. Then you have the load, DC supply. You have the load, the DC supply. Is it clear to you? That is the basis of that is the diagram. That is the representation, or what we can even call it model of a DC machine. Is it clear to you? So that is it. You have the commutator, you have the brushes, you have the stator, then you have the armature and armature conductors, etc. So that is that. In this other aspect, we are going to be talking more about this component that make up the DC machine. So I'm going to be explaining them one by one. I'm going to be explaining them one by one so that you understand it. So now, how we talk about DC machine? In DC machine, we are talking of DC generator and DC motor. Don't forget. Now, the construction of a DC machine, that's what we are now talking about here. Is it clear? I've told you the components. You have the stator, you have the armature coil, you have the bearing, you have the shaft, you have the commutator, you have the brush, and you have the windings. That is the coil. Is it clear to you? And the material is not shared. You would have seen all these things I'm talking about. I'm in page 11 now. So you would have seen all these things. So now, the DC machine mainly consists of two parts. Please write down. The DC machine, which I've told you that you have a DC generator and DC motor, consists basically of two parts. You have the stator and the rotor. Stator and rotor. Is it clear? The stator houses the feed winding, which is the source of magnetic flux in the DC machine. Is it clear to you? The stator houses the feed winding, which is the source of magnetic flux in the DC machine. That is the what they are talking about magnetic flux now. We are talking about the solenoid. Is it clear? We are talking about the solenoid. That is the wire that is coiled around a bar magnet. That why you will see all these things in if they have ever opened an electric pumping machine in your presence. Maybe those what they call those what that rewind a borehole machine, water pumping machine in a borehole. If you have ever been to your workshop before, this thing will not be strange to you. You will see that the magnet, very large magnet, the capacity of the machine depends on the size of the magnet and the number of turns of the wire that is wound around it. Is it clear? So I've told you that you have the stator and the rotor, and I've told you that the stator houses the solenoid. The other component, you have what is called the yoke. The yoke is an outer frame made up of cast iron or steel to provide mechanical strength and protective covering to the whole machine, and also carries the magnetic flux produced by the feed winding. That is the yoke. Is a component is here. Then you have the pole as component of a DC machine. You have the pole. The pole, this is the magnetic pole. The magnetic pole are made of thin laminations of silicon steel structure fitted onto the inner wall of the yoke with screws or weldings. The pole core carries feed winding. Is it clear to you? Then we have the feed winding itself, which is usually made up of copper wire. All these things are not strange. If we take for example excursion to common rewinders, to people that do rewinding, you will see all these things as very, very everyday things that they work with. So, but because we're in an academic class, all this may look strange to you. So, but most of you that have experience in this aspect even though you have a pumping machine in your house and you have gone to where they are repairing before, you will see all these things. So, feed winding usually made up of copper wire. Is the most common, is the best. Material that are made of copper, like even a generator, if you will be hearing people saying that this generator is copper, this Chinese generator they are selling all over the place now. You have Sumek Fireman, you have all this Pack, you have different types of Chinese generators that are in vogue these days, and you'll be hearing they will telling you copper. What they are saying copper, some of them they write copper on them, and telling you that the material is made up of copper, and you know that copper is a very good conductor of electricity. Is it clear? Yeah. So the feed winding is usually made up of copper wire wound over the pole slot and are connected in series. That is side by side, up and down. They are wound in such a way that when energized, they form alternate north and south pole, hence producing magnetic flux. Is it clear? Of a magnet. Then we have the eye bolt. It helps to shift the machine from one place to another for level change. That I'm now dealing with the components of a DC machine. Is it clear? So don't be confused. Now we talk about stator. I've told that the major component of a DC machine is the stator and the rotor. So now we have talked about all the components of the stator. And okay, let me go over them again. Since a DC machine is made up of a stator and a rotor, I've told you all the component of the stator as one. You have the yoke, you have the pole, you have the feed winding, and you have the eye bolt as the three component of a stator. And you have the diagram of a stator there. Is it clear? You have it there. Now we now go straight to rotor. Straight to rotor as one of the components of a DC machine. Now the rotor contains slots to carry armature windings and provide the rotating element in the DC machine. I come again. You know, when we are talking about anything motor, you people should know it from today that anything motor has to do with rotation. Circular motion. When you are hearing motor, even a car, this is why people call car motor, because it's just one component of the car that is called motor. What is the function of that component? It rotates. It moves in a circular motion. Is it clear? So a rotor, just like a motor, contains the slot to carry armature windings and provide the rotating element in the DC machine. So the movement that is the rotational movement. So now the components of a rotor, number one, you have the armature core, you have the armature winding, you have the commutator and the brushes. These are the three major components of the rotor, but I'm going to explain them one by one. I'm going to explain them little by little. Now they're cylindrical in shape with wires inside it, wound to and fro, that is to and fro at the other both ends, with a mechanism and move. Is it clear? That is the armature core. Now it is cylindrical in shape with slot to carry. Armature core is built up of thin laminated circular silicon for reducing eddy current loss. to prevent losses of Yeah, I didn't know I was muted. I've changed it. I've changed it. Yes. Sorry for that. I didn't know I was muted. So now I'm talking about, and I'm taking another subtopic. I'm talking about the losses in a DC machine, or losses in DC machines. You know, DC machines are electric generators and electric motors. What differentiates electric motor from an electric generator is the energy conversion part. Are you following? I cannot emphasize this one enough. The difference between a DC generator and a DC motor is the energy conversion part. Whereas in a DC generator, energy conversion is from mechanical to electrical via the magnetic field. In a DC motor, energy conversion is from electrical to mechanical via the magnetic field. Also, the DC generator is based on the principle of Fleming's right-hand rule, while that of a motor is based on Fleming's left-hand rule. That's why I want you to go to physics textbooks. You will see all these things inside there so that you will not be lost. So now we are talking about losses in DC machines now. I said that there are principally four kinds of losses that can occur in a DC machine. The four losses are as follows. Number one, electrical or copper losses. That is losses from the conductor. You know, the conductor, the copper is the one that is wound around the magnet. Then we have core losses. These are the losses from the core, that is the armature. Then we have the mechanical losses from maybe heat from the metals. From that, I was telling you about a shaft. I was telling you about a shaft just now. That shaft is a metal. Heat losses can occur from there. Then we have stray load losses. Take note of the four types of losses that we have. So I may take time to explain them one by one if we have time. Okay, but let me talk about the electrical or copper losses briefly. Copper losses are the losses that occur in the armature and feed windings of the machine. That is what I told you before. Is it clear to you? There are formulas for it. PA, that is armature loss. PA equals IA times ROA. That is current times resistance. Is it clear to you? Current times resistance. The current is squared. The resistance is not squared. That is I squared, I times I. That is the current is squared. Then the resistance is single. So I squared times A times R is the armature losses. Then we have the feed losses. Now we go to core losses. Core losses, we also call it magnetic losses. The core losses are losses encountered in the magnetic core of the machines, which include hysteresis losses and circulating eddy current losses. Is it clear? Now we now go to mechanical losses. I've explained these things. I'm just trying to make it better. Mechanical losses, there are two types of mechanical losses here. We have the friction and the windage. The friction, I told you that metals will be rubbing on each other, like the shaft. Other metals will be rubbing on the shaft. Now, when metals rub on the shaft, heat is going to be generated. So friction losses are caused by the friction of the bearing in the machine with the shaft, and friction force between brushes and commutators. While windage losses are caused by the friction between the moving parts of the machine and the air inside the motor casing. That is that. Now that will take us to stray load losses. Stray load losses, which is the last loss that we can experience in a DC machine. Is it clear to you? Yes. Now, stray load losses are losses that cannot be placed in one of the previous categories, such as loss due to distorted flows and short circuit current in a coil. So those are losses that are due to short circuiting the current in the coil. Is it clear? So that is stray load losses. So that is that. Now we are now in part 4 of this course. I'm actually using slides here. We are in part 4 of it, which is page 21. I suppose page 21. We are going to be talking about DC generator types. DC generator type. Mind you, we are just talking about generator. We are not talking about motor. DC generators are of two types. We have the separate and the self types. Please, I come types of DC generators. Topic that is page 20 rather, page 21. Types of DC generators. We have the separately generator and we have the self. Are you following? Now, separately excited DC generator. In this, we mean by separately excited, feed coils from a separate DC source. I come again. Excited DC generator. The feed coils are energized from a separate external DC source. This feed winding is electrically separated from the armature circuit. Is it clear? So they are different. They are different components. That way they will be separately excited DC generator. Then we have self-excited DC generator. In this type, feed coils from the current produced by the generator itself. In self-excited DC generators, the feed coils are energized from the current produced by the generator itself. Is it clear? Generated is due to the generated EMF causes a part of current to flow in the feed coils, thus strengthening the feed flows and thereby increase the EMF generation. So there is no external DC source for self-excited DC generator, whereas in the separately excited generator, we have they have an external DC source. That is the difference. So now, I think I need to explain this very important part, although it's practical. Now, feed winding and armature winding are interconnected in various ways to achieve the wide range of performance characteristics of a generator. Now, depending on that, self-excited DC generators can further be classified into two main types. I come again. I've told you that these generators are divided into two types. We have the separately excited and we have the self-excited. I have taken my time to tell you that the separately excited, in this type, feed coils are energized. That is those the coils. You know what we mean by coils? That is those copper that are wound around the bar magnet are energized from a separate external DC source. Is it clear to you? Whereas in a self-excited DC generator, that it is the generator itself that the current produced by the generator that causes the excitement or that excite the feed coils. Is it clear? There is no external source of DC source. So that is that. No, I'm now trying to let you know that self-excited DC generators are divided into two types. We have the shunt wound, that is SHUNT. These are electrical terms. If you do electrical very well in your secondary school, all these terms will not be strange to you. We have the shunt wound and we have the series wound. Now, in the shunt wound type of self-excited DC generator, the feed flux is derived by connecting the feed winding in parallel with the armature winding. Shunt wound, that is the winding of the copper wire around the bar magnet, is derived by connecting the feed winding with the armature winding. Shunt winding is made of and the resistance is kept by about 100 volts. It's only small, less than 5% of the rated armature current. Then we have the series wound. Feed flux is derived by connecting feed winding in series with the armature. Is it clear? See, in electrical, we have what is called series connection. We have what is called parallel connection. The formula for this series connection, the resistance for series connection is total resistance is resistor 1 plus resistor 2 plus resistor 3 plus resistor n. While in parallel connection, the total resistance is 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3, and dash equals 1 over Rn. Is it clear? So that is that about the various types of self-excited DC generators. Please make sure you write all these things down. We now continue. We continue with now we are seeing the cycle for separately excited. The arrangement for separately excited. Then we also have this the circuit for shunt and the shunt wound and the circuit for parallel for series wound. Now, mind you, I've told you that for shunt wound, that is in the example of self-excited DC generator, they are connected in parallel. Is it clear? They are connected in parallel. Why for the series? Please, I come again. I said for the self-excited that are divided into shunt wound and series wound, the shunt wound are connected in parallel, while the series wound are connected in series. And I've told you what it means to connect things in parallel and to connect in series. I've also told you the formula for calculating resistance in parallel and resistance in series. So before we go further, before the admin will tell me to stop, let me quickly give you your assignment for today. Yeah. Number 1, you are going to explain the basis of a generator action. Explain number 1A assignment for today. 1A. Explain the basis of a generator action. Mind you, generator is different from a motor. Explain the basis of a generator action. That is number 1A for your assignment. Number 1B. What are the losses? I told you there are 4 types of losses just now. What are the losses experienced in a DC machine? I come again with the assignment. Explain the basis of a generator action. That is the principle on which a generator is based. Which I've explained to you at the beginning of this course. I said a generator converts mechanical energy to electrical energy via a magnetic field. So you add things to it. You do research and add it to it. Then number 1B, what are the losses experienced in a DC generator? Is it clear? What are the losses experienced in a DC generator? I've told you that there are 4 types of losses that are experienced in a DC machine, or generator, if you want to call it, in a DC machine. I told you there are 4 types of losses. I said we have strain load losses, we have mechanical losses, we have core losses, then we have electrical or copper losses. I believe everybody wrote them down. So those are the 4 types of losses that we can experience in a DC machine. And I took my time to explain those losses. I said copper losses are the losses that occur in the armature and feed windings of the machine. I now told you that core losses, C-O-R-O-E, core losses, also called magnetic losses, are losses encountered in the magnetic core of the machine.